My name is Kevin Huang, and I'm a sophomore from Franklin Monroe High School, and I'm with my partner here.
Hi, my name is Eli Shealy, and I'm also a sophomore from Franklin Monroe High School.
Humanity has been gazing upon the stars for eons, always wondering what's out there, what's out of reach. And so we wanted to do this experiment so that we could once again recultivate our ambitions into space travel. As out there in space, we have unlimited resources that are limited on the planet we are now, the resources that we gain by poisoning our own planet, our own people. For example, there's an asteroid in space that has more gold than the entirety of Earth's history. And yet we choose not to explore space. Why? And so we want to do this experiment so we are able to once again actually truly conquer the stars. And innovations and understanding novel technology also goes into not only just rocketry, as you can see here, but also in terms of launching better space exploration with probes, and lastly faster travel even on Earth with new planes, as well as better aerojets for agricultural purposes or whatnot. But first we have to understand rocketry.
Now, understanding rockets isn't a very hard concept. It mostly bases itself off of Newton's third law. If you push on an object, the object pushes back. Now, the way rockets achieve this is by using a fuel and an oxidizer combined together. Once you ignite this fuel oxidizer mix, it produces hot gas. This hot gas then pushes on surrounding air, therefore generating thrust and lift, which then propels the rocket into the atmosphere. So to actually achieve generating enough lift to propel such a massive vehicle, you have to have a nozzle. Now, nozzles aren't very complicated. Essentially, you have a combustion chamber where your fuel and oxidizer is ignited. This then produces gas. This gas is a low pressure but very high temperature. As it moves away from the combustion chamber, it is diverged at a 15-degree angle in what is known as a throat. The throat helps to compress the gas and make it supersonic. But once you have the supersonic gas, you can't necessarily push as well. So by converging and then diverging, you have a high pressure gas that then expands outwards more, therefore helping to generate more thrust.
And so for methodologies, we've moved on to our lab. The purpose of this experiment was to test the effects of rifling on rocket nozzles, and if that would increase the overall efficiency and power of the rocket. We hypothesized that adding rifling to a rocket nozzle, just like in weaponry, will increase the overall power, stability, accuracy, and overall efficiency of the rocket. But first we must understand our variables when describing this experiment. Our independent variables would be the types of rifling we used. For example, we have a normal smoothbore, a throat rifling, and a exit rifling. And so moving on to our dependent variables, that would be our max speed, max apogee, average acceleration, and max acceleration. For our control groups, that would be the type of rocket we used, exactly the same. Our launch pad, same exact launch pad, along with the controller, as well as the conditions in which they were launched. And so as you can see here, the rocket nozzles, we had different generations via each experiment, as we had shipping errors. However, that did allow us to cultivate rapid innovation for every launch. Starting off, so these nozzles were designed using a mix of CAD programs as well as Blender. The rifling you see was from a Blender, and the overall design was from a CAD program. And so the first design worked alright. As you can see here, the prongs did not go high enough to rocket, making it very easy for it to just fall off, causing us to use a lot of electrical tape. And another thing is, as you can see with some of our previous launch attempts, the plastic that we used to print these were not nearly heat resistant enough to survive the power of the motors. And so that caused us to move on to our next one with improved prongs so they can actually fit on better, as well as the spray.
But this paint generally overall helped the ability of our nozzles. In this case, this nozzle here survived 3 flights with the paint compared to these earlier nozzles which did not have the paint.
And even with some of these broken ones, it wasn't actually due to the heat like with our previous models. It was just due to the crash landings with the parachute not deploying correctly, or if wind conditions were too terrible and the rocket ends up crash landing. This is a C65 rocket motor. For this to launch, you would need an igniter. The igniter is copper wire with some nichrome wrapped around, which is put inside the hole produced from the manufacturer, along with a plug so nothing falls out, which is subsequently set inside where the rocket hole is. My partner Eli can explain how this allows us to launch our rocket.
Thank you, Kevin. Now, it's a very basic concept. What we have here is the launch controller. On the inside are a few batteries. Now, you take these alligator clips here and connect them to the 2 copper wires. The copper wires help carry electricity to the nichrome. What's nice about nichrome is when you put electricity through it, it generates heat. This allowed us to generate enough heat to light the motors and also keep a safe distance away to maintain safety standards. Data from our rockets, we use this Jolly Logic altimeter 2. This is a highly advanced altimeter which can measure altitude of which apogee happened, max G's of thrust at any given time, max G's experienced in total, the total burn time of the rocket, and how quickly it descended back to Earth as the parachute was deployed.
And how we strapped on the altimeter on our rocket changed throughout our experiments. At first, we just used a zip tie that we strapped around here, and as you can guess, it's not exactly aerodynamic or great for altimeter. So later on, we changed it so we just cut open the top of our nose and just tape it here, as it provided a decent amount of space in which we could just put our altimeter inside and then tape around the edges.
So, in the data we have presented in these graphs, the results uncovered that throat rifling is the best performing out of all the nozzles we tested. The 3 nozzles being tested, of course, being smoothbore, throat rifling, and then the exit rifling. Now, in almost every aspect, throat rifling achieved better performance rates compared to everything else. It had 3 times the max speed compared to the other 2 nozzles, twice the apogee of the other 2 nozzles, and 7 times the flight duration, as well as the best peak acceleration. Now, smoothbore ended up being the median of the pack. It wasn't necessarily the worst performing, but it also wasn't necessarily the best performing. And then when it came to the exit rifling, we found that it was the worst performing by far.
Though one thing that the exit rifling did have over the other 2 was the fact that it had the best average acceleration during the boost phase. And one thing we have to look at from our data is anomalies. So even though the throat rifling performed the best compared to the rest. It also had the most egregious outliers. As you can see all the way to the top right hand corner, this yellow dot right here is very far away from the other two that we had. And contrarily, the exit rifling, which performed the worst, also had the most consistent launches. As you can see with patches of red all over here, being mostly contained in a certain area. The data that we had from our experiments must be taken into account of reservations, because as you can see on the scatter plot, outliers do persist in our experiment simply due to how inconsistent rocketry is. Even professional organizations and establishments like NASA, SpaceX aren't able to do 100% perfect flights. And of course, if we could have like other schools also replicating our experiment, it could heavily mitigate the issues of outliers. Even if we did take away outliers from our experiment, the throat rifling would have still performed the best, just not as egregiously like you have seen in our previous graphs. How other studies compare to ours is decently consistent. The other studies found that rifling to a nozzle does in fact increase the strength of like the overall thrust and power. And so why our results turned out the way they did was, well, in hindsight, it makes sense. Rifling on an exit nozzle causes spin and improves speed, but that spin also causes it to face more aerodynamic forces as the fins are constantly constantly facing air pressure as it rotates. And so why the throat rifling did so well in spite of that was simply because in nozzle design, the greater the ratio from how small the throat is to how large the exit area is, usually means an increase in efficiency and power. And so what rifling did for the throat rifling was that it was able to compress the gases just like how a smaller throat would. And so with those compressed gases, it was able to expel the gases with even more power, bringing the overall maximum speed and alpha-gig to a higher high compared to the rest of the nozzles. And so moving on to our conclusion.
So now, in conclusion, our hypothesis did align with what we tested out in the field. We were able to prove that rifling does have an effect on the efficiency of a rocket. Now, some improvements throughout our experimenting is prioritizing getting our parts on time to help lessen the time it takes in between trials. Also, we could try testing new 3D materials and coating said materials in better heat-resistant coatings, maybe trying different paints or even ceramics or aluminum, which we wanted to try. Now, progression will, this would be seen as us actually experimenting in a vacuum chamber, possibly in a laboratory, over your standard atmospheric test. We also would like to see, in the future, hopefully, a more diverse rocket testing with, a difference between solid rocket boosters and liquid fuel rockets. But if given enough time, hopefully we will be able to reach a better conclusion with our rocket testing and seeing if rifling, overall improves the efficiency of our rocket.
And yeah, we thank you for your time, just being able to just watch over our presentation and everything. And we hope you learned something from this.